Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over the solutions to the limits practice test. Be sure to download the test and go over all the problems before you go through this solution. Do not forget to visit our website at math.serve.com under AP Calculus to gain access to a wide variety of tutorials to prepare you for the AP exam. All right, let's take a look at question number one. Question number one, we are to find the limit as x approaches 9 of the square root of x plus 2 root x. Now this limit problem is something that can be evaluated with substitution. So what we're just simply going to do is evaluate this function when x equals 9. All right, so let's go ahead and evaluate it. Remember, this is an example of a finite limit. Okay, so how do we know that this is a finite limit? Well, is x approaching a fixed number? The answer is yes. And there are no directions involved, so this is a double-sided finite limit. So let's plug in the 9 into the function. We have 9 plus 2 root 9. And then if we simplify this, we'll have the square root of 9 plus 2 times the square root of 9, which is 3. And then let's go ahead and simplify further. 2 times 3 is 6. 9 plus 6 is 15. Since 15 cannot be reduced any further, our final answer is going to be root 15. All right, let's move on to question number 2. So for problem 2, we have to find the limit as x approaches negative 3 of 9 divided by x plus 3 over x plus 3. Now, if you take a look at this limit, it's a finite limit, of course, but when you substitute negative 3 into the denominator, what happens is that the denominator becomes 0. So there is some kind of discontinuity happening at that point. The question is, when x is negative 3, do we have an infinite discontinuity or a removable discontinuity? If it is a removable discontinuity, then we'll know that the limit does exist. If it is an infinite discontinuity, the question is it going to negative infinity from or positive infinity from the left or right? So if you have a vertical asymptote or an infinite discontinuity here, you have to evaluate the left and the right hand limits to ensure that they're both tending towards the same infinite value in order for the limit to exist. If one is going to infinity and the other is going to negative infinity, in that case, the limit will not exist. They both have to tend towards infinity or negative infinity in order for the limit of the vertical asymptote to exist. Now in this case, we do not know what kind of discontinuity this is, so what we'll do is simplify it as much as possible and then see if we can cancel out this discontinuity here. So what can we simplify? The denominator is completely simplified, so we have to look at the numerator. Can we combine these two? Let's go ahead and try that out. Put this over 1. The LCD of x and 1 is x, so we multiply this fraction by x, top and bottom, to have the same LCD. Okay? Now this becomes the limit as x approaches negative 3 of 9 plus 3x divided by x. Alright, and then in the denominator, divided by x plus 3. Now we have a fraction in the numerator. We want to divide it by the denominator. So what I'll do, for the sake of uniformity, is express the denominator as a fraction also. Okay? So now we are going to have the limit as x approaches negative 3 of the numerator. I can rewrite it in standard form and also factor out the 3. So we have 3 times x plus 3 over x. So I switch these around using the commutative property of addition. That's 3x plus 9, and then I factored out to 3. So we have 3 times the quantity x plus 3, the same thing as 9 plus 3x over x. Now dividing by a fraction means you multiply by the reciprocal. So we reciprocate the denominator and multiply it by the numerator. The denominator fraction reciprocated yields 1 over x plus 3. Now what do you notice here? You notice that this discontinuity x plus 3 is in fact removable. How do I know? Because you can cancel them out. X goes there 1, x plus 3 goes there 1. Alright? So we are going to be left with the limit as x approaches negative 3 of 3 divided by x. Now we are free to evaluate this limit by substitution because it does not result in a zero expression in the denominator. Alright, so let's go ahead and evaluate that. We're going to have 3 over negative 3 by direct substitution, and that yields negative 1. So that's the result of our limit. Alright, let's take a look at problem number 3. For problem 3, we have to find the limit as x approaches 4 from the left of the expression 4 minus x divided by the absolute value of x minus 4. Now this is a finite directional limit or one-sided limit. In this case, we are approaching 4 from the left because of this negative right here. Alright? So let's go ahead and rewrite this expression in such a way that it will enable us to evaluate this limit. So I'm going to have the limit as x approaches 4 from the left. Let's switch this around and put it in standard form. If I switch this around, I'm going to have negative parenthesis x minus 4 divided by plus or minus x minus 4. Remember, subtraction does not commute. Alright? It commutes with its opposite, so you can't just switch the order of subtraction. When you switch the order, as I did here, you must introduce this negative to compensate for the sign change. So negative quantity x minus 4 is the same thing as 4 minus x. Okay? And then the denominator, by definition of absolute value of x minus 4 is plus or minus parenthesis x minus 4. X minus 4 units to the left and to the right of whatever point you're looking at. Okay? Now, since we are approaching 4 from the left side, the value that gives the absolute value of x minus 4 is going to attain a negative value. Okay, so approaching 4 from the left, you think about 3.9, for example, and then you can see that if 3.9 is smaller than 4, you have a negative result. So what does that mean? This limit can be expressed further as a limit as x approaches 4 from the left of negative x minus 4 over, since we're approaching x minus 4 from the left, negative x minus 4. Now, let's see. We can reduce this, can we not? Yes, we can. Another thing to note is that had we plugged in 4 directly into the original problem, we'll have a 0 in the denominator, which we cannot simplify. It looks like an undefined expression. So that's why we had to do all this work of simplifying as much as we can. Okay? So let's cancel out the x minus 4s. X minus 4 goes here once, x minus 4 goes there once. So we have the limit as x approaches 4 from the left. Negative 1 over negative 1 is what? Simply 1, right? So the limit as x approaches 4 from the left of 1, this is a constant function independent of where x is going, so our final answer is going to be 1. Alright, let's take a look at question number 4. So for question 4, we want to evaluate the limit as x approaches 0 of the square root of x plus 3 minus the square root of 3, that entire expression divided by x. Now we can clearly see that by direct substitution we will have a 0 in the denominator, so it looks like we have a discontinuity there. So is it removable or infinite? An infinite discontinuity. So what we're going to do here is see if we can simplify this expression. If you see radicals, the first thing you want to think of, if you cannot evaluate by direct substitution, is rationalization. Can you rationalize the numerator here to see if you can actually cancel out this discontinuity, which will make it removable? So how do we cancel out radicals? We're going to make use of the conjugate, right? The whole idea of conjugate lies in the fact that if you have a minus b multiplied by a plus b, this is the factored form of what? This is the factored form of a difference of squares, a squared minus b squared. The same process here. If you can multiply this by a term that generates a difference of squares, the square root and this square root will cancel out. So that's why you multiply by the conjugate. So the conjugate here is the square root of x plus 3 plus the square root of 3. So the numerator and the denominator, square root of x plus 3 plus the square root of 3. Now, how do you find the conjugate? You just simply invert the sign in the middle. Okay? Remember, we already have a minus b, so you just invert the sign of the second term to get your conjugate, like that. So what we'll do here is just multiply the numerator out. Since the numerator is in the form a minus b times a plus b, so this is, you can look at it as a minus b times a plus b. If you multiply a minus b by a plus b, what do you get? Get a squared minus b squared. So that's exactly what we'll have here. We're going to have the square root of x plus 3, square root of x plus 3 squared, minus the square root of 3 squared. Alright, and then in the denominator, we are going to leave it unsimplified. Okay, leave it in a factored state. The reason being that we do not know if this 3 that's causing problems with continuity is removable. So if we distribute it, it's hard to cancel it out if it is in fact removable. Alright, so we'll leave the denominator in its unsimplified state, and then we'll focus on simplifying the numerator to see if we can extract or be left with an x. So if you simplify this, the square and the square roots cancel out. You have x plus 3. The same story here, the square and the square root cancels out, minus 3 divided by x times the square root of x plus 3 plus the square root of 3. Okay? Plus 3 minus 3 cancel out since you're opposites. Now you're going to have the limit as x approaches 0 of x divided by x times the square root of x plus 3 plus the square root of 3. Now what do you notice in this resulting expression? You notice that these two x's can divide out. So that tells me that this original x here is actually a removable discontinuity situation. Alright? So now that we've eliminated that discontinuity, let's hope that we do not have another issue, which is not possible. So we have that taken out, and then we're left with the square root of x plus 3 plus the square root of 3. Now we can evaluate this expression by substitution. We're going to plug in the 0 for the x's. So we have only one x. So this becomes 1 over the square root of 0 plus 3 plus the square root of 3. If you simplify that, you're going to have 1 over root 3 plus root 3, which equals 1 over 2 root 3 And then, of course, you can rationalize the denominator, rad 3, and your final result will be square root of 3 over 2 times root 3 times root 3. What is root 3 times root 3? Root 3 times root 3 is the square root of the product of the radicand, so it's root 9, which is just 3. So 2 times 3 is 6. So there goes your final answer, root 3 over 6. Alright, let's take a look at question number 5. So for problem 5, we're going to find the limit as x approaches negative infinity of x to the third times quantity x minus 1 times the quantity 3x plus 1, all that divided by the third root of x to the sixth times x to the third plus 1. Okay? Alright, now if you take a look at this limit, how would you classify it? This is a limit involving infinity, okay? It's an infinite limit where x approaches infinity. So whenever x is going to negative infinity or positive infinity, you want to look at the growth rate of the functions, and then that can help you determine the limit. Now, since we have a product of a factored form of a polynomial in the numerator, the fastest growing term in the expansion of that polynomial will tell us, will basically be the only term that we'll consider in the numerator. Same goes with the denominator. So what is the term with the highest degree in the numerator going to be? Well, it's what you get when you multiply x to the third by x and then multiply your result by 3x. Okay? If you want to waste time, you can expand the whole thing and take the first term, but we don't have time to waste, so we just want to be efficient here. So what we're going to do is multiply those terms. Why did I select those terms? Because in each factor, they have the highest degree. This factor stands alone as x to the third. This is the first degree term. This is the 0th degree term. So this, I'll pick x. And in this factor, 3x is the first degree term. This is a constant or 0 degree, so I pick that. All right. So if I multiply them together, I will have 3x to the fifth. 3x to the fifth in the numerator. Now in the denominator, the same procedure applies. I'm going to be taking the third root of the product of the terms with the leading coefficient in the factors in the denominator. So I'm going to take x to the sixth and x to the third. They are the terms with the biggest degrees in each factor. Multiply them together. That will leave me with the third root of x to the... Now what do you do when you multiply exponents with the same base? You add the powers, right? So it's x to the ninth. Let's simplify this further. We have limit as x approaches it, negative infinity of 3x to the fifth over the third root of x to the ninth is the same thing as x to the 9 over 3, which is going to be x to the third power. Okay, so now what are we going to do? We can factor out the constant, factor out 3, doesn't really play a role here. And then we're going to look at the limit as x approaches negative infinity of x to the fifth over x to the third. Now, since we're going to negative infinity, what we can simply do is we can reduce this these two terms right here. So using the properties of exponents, whenever you're dividing exponents with the same base, you subtract the powers, right? So x approaches negative infinity of x to the 5 minus 3, which is x squared. All right? Okay, now I can simply plug in negative infinity into this problem and actually calculate what the limit is going to be, but sometimes it's beneficial to first evaluate the sign before you plug in infinity. In this case, it doesn't really matter, so what I'm going to do is just carry out this substitution. So I'll have 3 times negative infinity to the second power. Notice that this square is going to impact this sign right here. So yeah, our answer is going to be 3 times infinity, which is equal to infinity. So that's the value of the limit of this expression as x approaches negative infinity. All right, let's take a look at question number 6. So for question 6, we have the function 5 to the negative x plus 6x to the third plus 5x over 2x plus 3 plus the natural logarithm of the absolute value of x plus 4. Alright, so for the A part, we're to find a simple basic function for the right behavior model. To find a simple basic function for the right behavior, or the right behavior model, the same thing. Okay, so before we go ahead and solve the problem, I need to go over two things real quick. First thing is the hierarchy of growth rates for functions. Let's put that on the side. You want to know that the slowest growing function that you're going to be dealing with, we're looking at as x tends towards infinity. Okay, so these are functions that are increasing. Ln x increases to infinity, but it's the slowest out of the growing functions. Next, we have the polynomial function x to the n, and then beneath that we have, after that we have the exponential function a to the x, and then the fastest growing function, of course, is x to the x. All right. So as you tend towards infinity, this grows the fastest, followed by this, followed by that, followed by this. All right. Okay. Now let's also note the steps. The steps for finding the end behavior model are as follows. So first of all, you're going to take the limit as x approaches infinity of each addend. Okay, so find the limit as x approaches infinity of each addend function. So basically, all the functions that you're adding, you're just going to take the limit as x approaches infinity for each and every one of them. Okay, and then next, for the functions that approach infinity, you're going to compare their growth rates. Okay, so compare growth rates of functions that approach infinity. If a function goes to a constant, then that function is not a model for the end behavior, okay? Because it's just a constant, it doesn't count. We're focusing mainly on the functions that grow, and out of the ones that grow, the one that grows the quickest will be our right behavior model, of course, as x goes to infinity, okay? All right, so let's go ahead and do that here. So in this problem, we have three functions that are the addend functions. We have 5 to the negative x, we have 6x to the third plus 5x over 2x plus 3, and the natural logarithm of 5 of x plus 4. So let's look at the limits. Let's change the color here. So what is the limit as x approaches infinity of the first term, 5 to the negative x? This is going to be, let's see, we can reciprocate because of this negativity here. So the limit as x approaches infinity of 1 over 5 to the x. If we carry the substitution, we have 1 over 5 to the infinity, which is 1 over infinity, and 1 over infinity is equal to 0. Okay? All right. So this one, at infinity, this one doesn't really act properly. It actually approaches 0, so it's of no consequence. We're going to ignore that. Now let's take a look at the other two and see if they tend towards infinity. So for the next one, we're going to look at the limit as x approaches infinity of 6x to the third plus 5x over 2x plus 3. Okay, now if you look at this, since we're tending towards infinity, you just want to focus on the quickest growing function in the numerator and the denominator. So we have 6x to the third and 2x. Those are the functions that grow rapidly in the numerator and the denominator. So this becomes a limit as x approaches infinity of 6x to the third over 2x. And then when you divide this out, or you simplify it, you're going to have limit as x approaches infinity of 3x to the second power. And then when you plug in infinity, you're going to have 3 times infinity squared, which is equal to 3. I'm sorry, which is equal to infinity. Now what you want to do is you want to pay close attention to what the function looked like before you evaluate it. You see this entire function, we simplified it to 3x squared. At infinity, this entire function behaves like 3x squared. Okay? The ratio of the terms with a bigger degree in the top and the bottom basically determines how the function behaves at infinity. So let's pay close attention to this because this is the basic function that models the growth rate of this function right here. Now let's take a look at the next one. We want to look at the limit as x approaches infinity of the natural logarithm of the absolute value of x plus 4. Okay, so we can just do a direct substitution here. We have the natural logarithm of infinity plus 4, which is the natural logarithm of infinity. As you tend towards infinity, how does a natural logarithm function behave? It tends towards infinity, albeit slowly, right? So this is also infinity. So the first term doesn't really count. These two are the terms that grow towards infinity as x approaches infinity. So now what we're going to do is basically compare the two functions. Which one grows faster? Is it this polynomial function here or the logarithmic function? At infinity, this behaves just like 3x squared, so we can focus on this. So which grows faster, 3x squared or the natural logarithm of x to the fourth? Those are the two we're comparing. If you go to our hierarchy, we can clearly see that the polynomial function, x to the n, grows faster than your logarithmic function. Logarithmic functions are like the slowest ones, okay? So in this case, the right behavior model is going to be given by this function right here, 3x squared, okay? So the right behavior model is 3x squared. So what does this mean? This basically means, let me state the significance of that. The meaning is that the limit as x approaches infinity of the original function divided by 3x squared is going to be what? Is going to be 1. That's what it means to be a right behavior or left behavior model. Because if you take the limit as x approaches infinity of the function and that model, the growth rates are exactly the same, so it just basically becomes 1. So that goes the right in behavior model function. Alright, now let's take a look at the B part. For the B part, we are going to be looking for the simple basic function for the left-hand behavior. Okay, so for the B part, we're going to find a simple basic function for the left-hand behavior. Okay, left-hand behavior. So in the left-hand behavior, we're looking at the limit as x approaches negative infinity. All right, so which function will cause the quotient of the original function and that function to equal to 1 as x tends towards negative infinity. We're going to be using exactly the same procedure as we did earlier, but the only difference here will be that we're going to be approaching negative infinity as opposed to approaching infinity, okay? So let's go ahead and rewrite the original function we had, 6x to the third plus 5x over 2x plus 3 plus the natural logarithm of the absolute value of x plus 4. Okay, so now we're going to evaluate the addend functions to find the limit as x approaches negative infinity. So for the first one, we're going to do the limit as x approaches negative infinity of 5 to the negative x there. And then this, you can express this as the limit as x approaches negative infinity, reciprocate that of 1 over 5 to the x. And then we can do a substitution here. We'll do a substitution. We have 1 over 5 to the negative infinity. What on earth is this? Well, this is equal to 5 to the infinity. Because of this negative right here, it basically indicates reciprocation, okay? So what's 5 to the infinity? That rapidly goes to infinity. So this right here is a candidate to be considered. You notice for the right end behavior, right? That wasn't a candidate. It went to 0. But going to negative infinity, this actually is in the game. Okay? Now let's take a look at the next function. Limit as x approaches negative infinity of this function right here, 6x to the third plus 5x over 2x plus 3. We've done this before. We know that at infinity, just these two play a valid role. So we're just looking at the limit as x approaches infinity of the quotient of these two, which is 3x squared, as we did previously. So this is going to be 3x squared, right? And then when you plug in infinity by substitution, you have 3 times negative infinity squared. You see this square right here negates this, makes this negative a positive, right? So you just have 3 times infinity, which is just infinity. So this is also a candidate to be considered for comparison. Last but not the least, we're looking at the limit as x approaches negative infinity of the natural logarithm of the absolute value of x plus 4. Alright, so we can just substitute here. So we have the natural logarithm of the absolute value of negative infinity plus 4. So negative infinity swallows 4 up rapidly, so we have the natural logarithm of negative infinity, natural logarithm of the absolute value of negative infinity. So the absolute value does its job on the sine here. So this is just simply the natural logarithm of infinity, which is equal to infinity. So guess what? This is also a candidate for consideration. So all three of them are candidates for consideration. We have the exponential function, we have a quadratic, and a logarithmic function. So if you remember your hierarchy, which one grows the fastest out of the three? Let's go over our hierarchy again. We said that the slowest one is the logarithmic function, followed by the polynomial function or power function, followed by the exponential function, and then the fastest is x to the x. So if you look at this right here, this is the fastest growing one because it's an exponential function. All right. So let's go ahead and write down our answer. The left end behavior model. The left end behavior model is what is it again? 5 to the negative x. 5 to the negative x. Okay, because it dominates. What does this mean? What is the meaning of that, considering the definition of what it is to be an end behavior model? The meaning of this is basically that the limit as x approaches negative infinity of the original function, divided by 5 to the negative x. Guess what that's going to be? That's going to be 1, because they basically match each other in growth rate at negative infinity, so their quotient is just going to be 1. Okay, so that's what it is to be a left-hand behavior model. So thanks so much for taking the time to watch this presentation. Really appreciate it. Do post a comment to let us know what you think about this clip. And if you have any questions, just put it down in the comment section. I'll be glad to address it. And also let us know what you think about this presentation. More clips can be found on mathcodeserve.com under AP Calculus. Thanks again for watching, and have a wonderful day. All right, let's take a look at question number 7. So for question 7, we're to find the limit as x approaches 0 of sine 5x over sine 2x. Now this limit can be evaluated using the Squeeze Theorem, which is based on the idea that the limit as x approaches 0 of sine ax over ax is equal to 1. Alright? As long as the denominator and the argument of your logarithm are identical, then the limit as x approaches 0 is basically 1. There is also another shortcut you could use to evaluate a limit of this nature. So this is a formula that's dependent, that's derived from this formula right here. Limit as x approaches 0 of sine ax over sine bx is simply a over b. Alright, so if you look at this situation, you can just automatically conclude that your limit here is 5 over 2. Alright, well, let's go ahead and do it the long way. I'm going to show you using the Squeeze Theorem that that this limit is in fact 5 over 2. Okay, so to do that, first thing I'm going to do is I'll rewrite the numerator and the denominator. I'll write the numerator as sine 5x over 1, okay, over sine 2x over 1. Now the goal here is I want the denominator and the numerator expression to be identical to the sine argument 5x. Same goes with the denominator fraction. All right. So in order to make the denominator and the numerator identical to 5x, I will have to multiply the numerator by 5x over 5x. Same story with the denominator. I need 2x down here, so I'll multiply by 2x over 2x. So I'm certain that I'm not changing the problem because I am just multiplying by 1. Alright? So this is how I'll arrange it. I'll in fact take this 5 and insert it in front of the sine function, and then this 5x goes in the denominator, and then this 2x goes in front of the sine function, and then this 2x goes in the denominator right here. So I can then write this expression as the limit as x approaches 0 of 5x sine 5x over 5x divided by, and then the same setup for the denominator, 2x sine 2x over 2x. Alright? Now what you notice is 5x and 2x, I can divide out the x's. X goes here once, x goes here once, and I can factor it out of the limit as a constant, so we'll have 5 over 2 times the limit. Now I can take the limit of the numerator and the denominator. Okay, so we might as well just do that. We can distribute the limits to the top and the bottom. So times 5 over 2 times the limit as x approaches 0 of 5x, of sine 5x, of sine 5x over 5x divided by the limit as x approaches 0 of sine 2x divided by 2x. Now we can now use the squeeze theorem that we considered earlier. See, if the argument of your sine function and the denominator are identical, the limit as x approaches 0 is 1. So we're going to have a situation where we have 5 over 2 times the numerator becomes 1, the denominator 1 also. 5 halves times 1 is simply 5 over 2. Okay, so that's the value of your limit. All right, let's take a look at problem number 8. So for problem 8, we have to find the limit as x approaches 0 of 5 cosine x over x. Okay, so in this case, I can factor out the 5, so I have 5 times the limit as x approaches 0 of cosine x over x. Now we remember earlier that we stated that the limit as x approaches 0 of sine ax over ax, so we can just let a be 1. So we have sine x over x. The limit as x approaches 0 of sine x over x is 1. Alright, but for the cosine function, the limit as x approaches 0 of cosine x over x does not exist. Okay, most people think that this squeeze theorem applies to cosine also, and the answer is no, it does not. Alright, so this limit right here does not exist. Okay, so the limit does not exist. All right, now let's move on to the next problem, problem number 9. So for problem 9, we have to find the limit as x approaches 0 of 1 minus cosine x over x. Okay, now obviously if we evaluate this limit by direct substitution, we're going to have a 0 in the denominator. All right, so that doesn't necessarily mean that the limit does not exist. We can try and simplify this into a form to see if we can evaluate the limit. Okay, so let's go ahead and multiply it by, I'll multiply it by its conjugate. So 1 minus cosine x, I'll multiply by 1 plus cosine x, and then 1 plus cosine x. Now you might wonder, why did I do that? Well, because if I expand it, I can make a trigonometric substitution using the Pythagorean identity. All right, so if I simplify the numerator, I'll have limit as x approaches 0 of 1 square, which is just 1, minus, you have minus cosine x plus cosine x, those two cancel out, and they have minus cosine square x. That goes in the numerator, and then in the denominator, we have x times 1 plus cosine x. Okay, now let's go ahead and simplify that further. We're going to have the limit as x approaches 0. Now this identity 1 minus cosine square x, if you look at your trig identities, that's the same thing as sine square x. Okay, that divided by x times 1 plus cosine x. Now sine square x can be broken down into the product of two sine functions. So we have the limit as x approaches 0 of sine x over x times sine x over 1 plus cosine x. All right, now we can take the limit of these two factors right here. So this expression now becomes, let's see what it becomes. It becomes the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of sine x over 1 plus x. Alright? And what do we have here? Now we can use the squeeze theorem here. If we apply the squeeze theorem here, if I do that, I think I changed the problem a little bit. Let's fix that. 1 plus cosine x. Sorry about that. Alright, so applying the squeeze theorem to the first limit, the argument of your trig function is the same as the denominator, so the limit as x approaches 0 of that situation is just 1, using our squeeze theorem. And then here we can evaluate this limit by substitution. Alright, so we'll do that. We're going to have sine of 0 divided by 1 plus cosine of 0, which is 1 times sine of 0 is simply 0 over 2, because cosine of 0 is 1, and then 1 times 0 is simply 0. Okay, so that's the limit as x approaches 0 of 1 minus cosine x over x. Alright, let's take a look at the last question, question number 10. So for problem 10, we want to find the limit as x approaches 0 of 4 minus x sine 1 over x to the third. Okay? Alright, so this one we're going to be using the squeeze theorem in a different way. So let's go ahead and do this. So let's see. First thing we want to start with is by acknowledging the boundaries of the sine function. We know that the sine is bounded between 1 and negative 1, regardless of what this denominator is. So let's go ahead and write that with an inequality. We have negative 1 is less than or equal to sine 1 over x to the third. That's the range of your sine function. We know that from trig. Alright, so what we're going to do now is we're going to attempt to create this limit expression right here in the center. Alright, and then we're going to take the limit of the exterior resulting expressions and then see if we can have a sandwich situation here. So let's go ahead and do that. So what are we going to have? We're going to have, alright, so let's see. In this expression right here, we have an x being multiplied by sine. In fact, we have a negative x. So let's see. We can multiply all three terms by negative x. So let's go ahead and do that. But one thing you want to note is that if you multiply an inequality by a negative sign, the orientation of the inequality reverses. Alright? So if I multiply by negative x, all three sides, so negative x times the left side of the complex inequality, and then negative x, ooh, I have to change the inequality symbol. So if I multiply by negative, I have to invert the symbol. And then times negative x to the center expression. And then reverse inequality, negative x to the last number, which is 1. Okay, so if I simplify that, I'll have x is greater than or equal to negative x sine 1 over x to the third, and that's greater than or equal to negative x. Okay, so I can reverse the inequalities again. So I have negative x is less than or equal to negative x sine 1 over x to the third, and that's less than or equal to x. Okay, now there's still a 4 there, so let's go ahead and address that situation. We have to add 4 to all three sides of our inequality. Okay, so I'm going to be adding 4 here, adding 4 there, and adding 4 there also. So that's going to yield 4 minus x as less than or equal to, is less than or equal to 4 minus x sine 1 over x to the third is less than or equal to 4 plus x. Okay, now what I'm going to do now is I'm going to take the limit as x approaches 0 of all three sides of this complex inequality, okay? Let's go ahead and do that. So we're going to take the limit as x approaches 0 of 4 minus x less than or equal to the limit as x approaches 0, 4 minus x sine 1 over x to the third less than or equal to the limit as x approaches 0 of 4 plus x. Alright, so what do we notice? If you find the left and the left and the right limits, what you find out that is you plug in 0 here, you have 4 minus 0, which is 4. 4 is less than or equal to limit as x approaches 0 of 4 minus x sine 1 minus x to the third less than or equal to, if you plug in 0 here, by substitution, you also get 4. So this limit, which is the original problem, limit as x approaches 0 of 4 minus x sine 1 over x to the third is between 4 and 4. So if you're between the same number, you have to be that number, okay? So by the Squeeze Theorem, Squeeze Theorem, the limit as x approaches 0 of 4 minus x sine 1 over x to the third is equal to 4. Okay, because if you're between 4 and 4, you must be 4. So that's basically that. So thanks so much for taking the time to go through this review test series. Do subscribe to our channel for updates to other cool AP Calc tutorials such as this. And please post a comment in the comment section below to let us know if you still have any misunderstandings, clarifications, or if there are any suggestions that you have to help us improve the quality of our presentations. All right, thanks again for watching, and do visit our website at math.serve.com.